Martin, for inviting me. What I'll talk about this work, it started roughly speaking in 2022 with Sam Campbell brothers. But many people have contributed for many names here and see their work and ideas. In the lecture, I should say that somehow the travel from Zurich to Frankfurt is just perfect. I leave the office, go to making their coffee, open my notebook to write a lecture, and then by the time I arrive, it's all finished. I don't have a 4-hour lecture. So we're going to talk about AV, and AV is a module, I say, is principally polarized between the varieties. If you're an algebraic geometer, the way to think about this is a moduli problem of a pair, abelian varieties of dimension V. Some kind of complex source, but with an extra data with a discriminative polarization. And it's a moduli problem of that. There's another way to think about it, which is somehow more topological or complex geometry. Is you can take the medial upper half space and sort it by the simplicity. And if you look at these, so there's two ways that are somehow equivalent. So if you're an algebraic geometer, somehow this is the state of moduli problem. And that should just be the answer. But in fact, there's a way that looks at this space, it can make explicit quotient. It's very helpful, and it makes a connection. The connection is maybe the beginning of the problem. But there's this group here that's connected to the geometry of AV. And the very first thing that comes with this legal upper half space is contractible. If you're working with Q coefficients, if you're interested in the homology, group homology. There's some stuff. In particular, we can take the stable point. This is computed by Varel. 1972, and it's equal to the trig algorithm on certain classes. What are these? These lambda classes. And so then I use the algebraic geometry picture to define them. That if you look at AG, is a universal abelian variety and has a zero section. And there's from this geometry, there's the Hodge bundle. The Hodge bundle is the bundle on the moduli place of a given variety, and it's defined to be the pullback to the zero section of the relative cotangent space. The rank P bundle. Forward? No. Oh, pull it back. Oh. You look at the zero section and look at the cotangent space. And what these lambdas are the return classes. You might wonder why there's only odd ones, and we will see later something about it. Keep it on the shadow. Okay, so this stable cohomology computation by Varel inspired Erhard Knacker here some years later. The definition to define the topological algebra classes are vague, and we consider it inside town. And this is by definition the subalgebra generated by lambda. So this definition parallels the way topological rings are defined in the moduli space of curves, and I'm not going to go discuss all of the motivation there. But that's his definition, and he has a nice theorem theorem 1996. Seems like a long time ago, but actually, for me, I remember this like it was yesterday. In any case, 1996, then the theorem says that he computes what this ring is. It's generated by all the numbers, and it has two types of relations. The first relation is energy to zero, and the second is a system of relations, which are called complete relations. Which is if you take the total Chern class, the Hodge bundle, and multiply it by the dual, and it gives you one. So this gives many relations in the lambda for this experiment. And in particular, if you look at the very first one, let's see, the total Chern class, the Hodge bundle looks like one, and so on. The total Chern class of the dual is basically the same thing, except you have to change some sign. And if you expand this, you expand the product, well, get you out of 1, and then in codimension 1, in the first grading, it's just capital, there's nothing there. So, well, 0, and you get no relation. For the next one, you see you get 2 lambda 2, and then you have minus lambda 1 squared. So this is a relation. And if you see what this relation does, it says that you didn't really need to have lambda 2. And this is kind of why you follow this logic. You don't need to. Okay, so that's the theorem. And actually, what's not apparent, immediately apparent in that theorem, is how nice a range this is. So the algebra that Herard defines and computes is actually a Goranskian moduli with Sokal in degree B choose T. Which what this means is that if I look at the B choose 2 part, this is isomorphic to Q, and what this means will be discussed in a moment. It's actually an important part of this lecture. But anyway, it's isomorphic to Q, and if you look at pairings into that, then they satisfy duality. That's what this one means. I should say, maybe I should have said this at the beginning, that the dimension of AB is also binomial. It's not this binomial cluster. It's B plus 1 to 2. And the difference between, it will be also relevant if you know your binomial coefficients. The difference is G. That's kind of a surprising thing. The tautological rings have been defined in many situations, and more or less, one has to be very lucky to find them to be currency local. But it's a very important fact for us. Okay. So I'll say a little bit more about it. But the statements about the algebra now are just statements in commutative algebra in the sense that once the ring is identified, and more or less everything I say about it you can work out by yourself. There's no using geometry on one presentation. But some facts that are nice is that you could say, well, I said that this codimension B choose 2 is one dimensional and what's a generator? Well, there's a very nice one. like the product of all the classes, all of them, and that's the sum. It's the degree is the sum of the integers from 1 to 2 minus 1, which is also G2. This is the stuff over here. And that's also not zero. Something else which is nice to know is that you can, if you want an additive table of the algebra, you can obtain one by just taking monomials and the lambdas raised to some powers, where these powers are always either 0 or 1. So it's some kind of minimal monomial, degree 1 monomial basis. And then this shows the fact of the dimension, the total dimension of this algebra is 2 to the minus 1. So anyway, it's a very nice algebra, a very simple one to think about. In some sense, much easier than the parallel algebra that comes out in the modulus first. Okay. Having some review of errors results, here results. So we've already seen this connection from complexity. And the first geometric connection for AG to other moduli spaces or other mathematics is moduli space of curves. And this is by the Torelli map. Here, one thing one has to be careful is that often when the Torelli map takes a curve, to the pair, this Jacobian C with theta, this is principally polarized in variety. And one should be careful here not to do exactly what I've done here, which is just not for just smooth curves. That's a bad idea. It's a bad idea for 2 reasons. One is that if you do it for just smooth curves, there's a map here. So the Torelli map. If you do it for just smooth curves, this map is not proper. And that's bad if you want to ever push forward anything. And another thing is if you do it for just smooth curves, then the space on the left here will have too many holes, and roughly speaking, everything I calculate will fall out of those holes. So it's very important to have compact type here, and compact type means you look at curves and blue graphs. Sorry, this C is compact type. So there's a connection, there's a really basic connection. It's one of the oldest connections in all break down curves and different varieties. And so on the other hand, these theory of classes have been studied a lot on the curve side. So if I put here M, the compact type, and here G, so there's a notion topological algebra here also. And I explained to you what the notion is here. I won't define this, but it involves looking at all the strata and the kappa classes, the cotangent lines. Adrian didn't even define the cotangent lines, so maybe we don't define this down here. But it's the algebra with what's called topological classes. And here I gave so there's a complete presentation. Here. Well, the analog here is, this is still an open question, but there's a complete proposal. So that's a whole subject, which I'm not going to really go much into. It's much more complicated. So this is Gorenstein. This is known to be not Gorenstein. Meaning both Dixon's proposal can go checked is not Gorenstein, and also the fact that it's actually proven to be not Gorenstein in several cases. But it is the case. So here we see it coming together. There is nevertheless something like a social. That's the highest degree where it's not 0. And here it's not 2, and this is a little bit like 0. Okay, and somehow the first point of this lecture is that, so what happens on this side, it's not just that the Q, it's a canonical isomorphism. And that comes by an evaluation map. There's a canonical geometric evaluation map. Okay. The canonical map, and that map is having a somewhat interesting construction. If I take a class here, alpha, or I take a class, and I need to get a number out of it. And I want to do this by integration, but I have a small problem here because this compact type space, even though it's called compact type, it's not compact. And so the way that this is done, this evaluation of alpha is defined to integrate over m bar. You take alpha, but alpha it's not defined on m bar, so you have to extend it in some random way. Lift the class. There's a price to pay for that. And then then it's codimension 2g minus 3, and mg bar is 3g minus 3. But that difference is also g, which is good. So I can put 9 with g here, a high level there. So this is some number. And to prove this is well defined, because I've done something drastic here, I've taken a random extension. Prove this is well defined, you need some geometric property. So we need some value. That vanishing is old. It's something that we've been using in modulus basic curves to come back here. I'll write the vanishing, and it'll suggest an analogous statement for union varieties. Seems peculiar to spend so much time on this evaluation question about, as I said, from the algebra, you know that the so-called isomorphic that I spend a lot of time to show it's not just isomorphic, it's canonical, and you'll see why it's so. In order to make that an integral well defined, you can expect that you need it on the modulus space of curves within one person application. If I take the top 3,001 function and I restrict it to the full space minus compact type, this has a name jumping up and push it to be 0. So this vanishing holds, and this implies that the evaluation was well defined. And it's easy to see why that is, roughly speaking, since this lambda g doesn't care what the extension is, because two different extensions differ by something here. So this doesn't matter.
But if I choose another extension, they would differ on something of.
They'll differ here. It doesn't matter.
Yeah, but that is volume 0. No? Okay, I mean that's an integral, and the two integrals differ by something that has volume 0.
Yeah, but that's not how it works. No, I mean, every algebraic cycle is volume 0. This argument shows that every.
Let's stop the magic.
This is what you need. You need this thing. And an analog for AG is that you need, so we want to find an evaluation map. We'd like to define an evaluation map for the social here. And if you understood this for what happens for MG, it's kind of clear how you should do it. take some class on the modulus of abelian varieties, and we'd like to define it by an integral. And so the first issue is what do we integrate over? And there you should pick some compactification. And here, so there's some question about that. That's the first point. Then we should extend this somehow, the compactification, and multiply by lambda g. So it's sometimes formally just the same. But for this, you need to prove that the construction of this number doesn't depend on what compactification you take and what extension. And so for that, so one has to be a little bit careful. There's a class of compactification, toroidal compactification. I'm not going to say much about this. And so the same that you pick your favorite toroidal compactification, and then the geometric statement that the Hodge-Bundle extends, so this lambda g makes sense. And then you still have to worry about this extension here, and that is solved by the corresponding banishment. So this is this theorem that we in the fall. It's canning, and the theorem says that this is exactly the same statement. Lambda g, if I take the toroidal compactification, and I take out AG, this is vanishing, it's actually anyway. There's something philosophical that happens here also. It's like sometimes with MG, we always go to MG bar. There's no struggle with that. It's a normal compactification. Everybody likes this space. But the fact that it's so perfect leads to some crippling of imagination. Because here we have a situation that it's not clear which compactification checks the two. There's many of them. And in some sense, there are many here also we just didn't think about. And to put those pictures together, the most natural way is this language for cycle theory, this London and Tau theory. That's not a direction I'm going to go, but this is the first time you see this kind of difference in the relation to the compactification. Okay, so anyway, the outcome of this is which compactification? I plan to take any toroidal compactification. So anyone you like, you take or anyone you don't have a name, you take that one too. That's somehow the point. I don't want to be wedded to any single one. I want to do something that's intrinsic to these here.
And the proof of the theorem goes by using which toroidal compactification?
Or we don't use any one. So actually, the proof of the theorem, right? I'm not going to talk about the proof, but there are people here. Yeah, but those will be a 4-hour talk. But the proof of the theorem is you give me toroidal compactification, and then this toroidal compactification is fixed in various ways. Like bigger toroidal compactification from secondary reduction until the total space is reasonable. And on that total space is the residue argument that's made to get a closely defined. So that paper is on our side. That's one of the few things I'm talking about actually on the other side.
You know, is that true also for MG? So if I choose any
yeah, so that's it. Just want to start at the bottom. Okay, so there's a lot of talking to start with. The very first thing you could say, well, what is the valuation of my generator? This is some canonical number. What is this? And this number was calculated actually, more than 20 years ago. Right? I don't know when it's like a long time. This appears in Van der Geer's paper, but and it's equal to the product from I for 1 and B of million. That's the positive. So that's the answer there. And you can say, well, how do you do this answer? I'm not going to really go in this direction, but how do you use this thing called this person-for-comfort proportionality? That's a very nice direction to go, but I want to point out a question here. So actually where this comes from eventually is there's a calculation of one polar characteristic of AG. And this is by Ziegel. And this is written as a product of beta value. And there's some argument that eventually takes this calculation back, which I'm not going to give you today, but it already shows that something's kind of interesting with this evaluation. The question I want to make here is that people in the audience probably know that the famous calculation of the orbital data characteristic of energy by R, which is also a data value. Maybe here you have to divide and this kind of triumvirate of really basic moduli spaces and algebraic geometry. There's a third one in this kind of family, which is the moduli space of primitively polarized K3 surfaces. And here's the question: what is the local characteristic of that? So that's a question. I don't know. That was a total of 5. And it's not relevant to this lecture. Things like that. Okay, so maybe while I'm erasing, I can say some other question. So a question that's like that in terms of this log child cycle here, maybe someone will talk about it in this conference. I didn't look at it, but a question that one could try to calculate is calculating lambda g, which plays kind of a major role in this lecture. To define the formula for lambda g and the logarithmic child theory of kg, tracking all these toroidal compactifications. That's kind of an interesting question. I'll be there to try to find a formula for that, which lists takes a formula like LV MG bar, you know, that's also in the side. Okay, so maybe now back to the main direction of the lecture. So this was some work, and eventually we have this canonical projection, we have this canonical evaluation. And if you think about how I defined it, this also works here. You can take this evaluation for any stuff. Just an integral. And I want to now define projections. So here's the define projection operation. So what does this mean? I want to define the projection operation. You give me a cycle on and the projection operator gives you a velocity class on and how does this work? So if I start with the cycle, on the cycle I get a linear map. On topological cycles, a linear map is defined, so I can tell you what happens if I feed it from a logical class, and then the answer is I take the evaluation. Define some toroidal compactification. You extend out there. Extend data. So this is a linear function. But by duality, there exists a unique class of projection of alpha in the chronological such that this linear map is equal to the same linear map defined by these are as so that's the definition of this. We can check that this is a projection operation twice. It's topological, now we're good enough to start. So this construction has this amazing feature that if you give me any dot plot, any discrete dot plot, then you can write it canonically as the projection. What the projection does is you get the projected part and then something in the kernel of that projection. It's non-topological. So this is an element of the topological algebra, and this is something whose projection is 0. So it gives you a way, it gives kind of an immediate enumerative geometry of all of these cycles. You can give me any cycle you want, and there's a question, what is its topological part? And that question has an answer within this algebra, so that means an answer to polynomial and lambda. So the way that I like to think about this, especially if you I mentioned this before, and when Jung lived in Zurich for most of his career, and you can do this in kind of Jungian psychology. Here's the class, this is the ego, that's the part that it likes to show the world. And this is the Jungian shadow. It's in the subconscious, what's going on underneath. And actually, if you read Jung, you might think it's mathematicians. We must be computing more than Jung. But it's not true. Jung makes some computations. For example, he computes the shadow of the narcissist with the vampire, which signifies despair. But you'll see that the way these classes work is that they hide their shadow. It's hard to find. And another question that's very natural to ask is, why don't I have this for the moduli space recursive compact type? That there is no projection operator and there is no shadow there, and the reason is that the topological ring there is not satisfied the values as used crucially in the construction. So all of this vanishing and all of that is exactly parallel. The part that is not parallel in this construction, you see that there exists a unique person there for the linear function that fails for curves. There's some these things that are true, but they're much less used. But for abelian varieties, the matter is perfect on the moduli space of abelian AG. Every cycle class has canonically a topological part and a purely non-topological part of the shadow.
Is it known whether this projection is given by some algebraic correspondence?
I don't know. Yeah, but correspondence to where though?
Yeah.
Correspondence. It's a good question. Okay, so. But there's a lot of things to say now about this. So I wanted to say 3 things about how this projection appears in the study and what you can do with it. And roughly speaking, these 3 things are basically, so one has to do with Pirelli. And another one has to do with related to Lagrangian-Grassmannian. So about the Pirelli, the words of the Lagrangian-Grassmannian usually affects the number of elements. And then there's another one which is maybe the craziest. It has to do with another function like that. And this is related now to the quantum homology. So I wanted to say a little bit about how projection plays. So these are and so I won't say very much about each one because I don't want to take 4 hours long. So let's start with around discussion. So how, or maybe more generally, let's say even more generally, as I said, if you pick any cycle or cycle class inside AG, well, if I take any cycle, I get a cycle class. And then from the cycle class, I get a projection. And it's given an non-homological part. In other words, this non-homological part can just be written as the cycle and this construction is a way of making lots of very interesting cycles. The cycles are in this language purely in the subcontinent, they're all under the other cycles. So you could say, well, let's try to do some of that. But what's the simplest cycle we can write on AG? Maybe this is a matter of taste, but one of them would be A1, say G minus that maps to AG, and it's similar to the cycle. That is called B. Or maybe one can say any partition with B. B1, B2, L. Here's maps to AG. So this is a little library for every partition in B. There's some partitions. And so we can ask, what is this story look like here? And so the first one, this cycle, while it looks completely innocent. So that's while it looks completely innocent, we can try to the question here, the first question is what is the projection? And what about so the first thing is what is its projection? So let me do that second. So let's first look at this interesting cycle that I said. So it's like delta G, and it's the product minus the projection. So that's great. It's a purely shallow one. And the question you can ask about this, of course, the very first one is it on zero? That's pretty much the most basic question. And the result from last year is it's not all of it. Now for the non-homological part, it's hard to ask the question, what is it? In some sense, that equation tells us the cycle minus the projection. But to ask what it is in some other language is hard because you need to know some library of non-homological classes. So we're not prepared yet to ask what it is, but we can ask whether it's zero or not. That's a question you can ask about any cycle.
What's the smallest degree in which you can hope to have a non-zero shadow?
This is for this size G equals 6. It's not only the smallest one, but technically it's the only one.
No, for a given G, the degree, the codimension.
Ah, what are you saying? That everybody has?
No, when can you hope? We cannot.
Yeah, probably not for dimension 2, dimension 3. I don't know. There's been some results about Chow. I don't know. They not great for people. But my guess is you have to be because 5, 6 something. Okay, so the claim about this is so we want to know whether there is a question about and how are we going to check it? We can pull back the cycle Borelli, and it's good luck that this cycle is actually quite well to the class on modulus basic cursor contact type. So these results I'm going to say here are all with Stan Canning. So this is good luck. That's not going to be true. for any cycle on AG. This cycle is good luck, it's here. And then you can try to see whether it's zero or not. So this gives us, so somehow this space is bigger, in some ways bigger. So it gives us more tools to show it's not zero. And it turns out that for G fixed, if we can prove it's not zero. And for the higher G's, so G equals 7, something magical happens and the subtraction vanishes, so I don't say anything about that. So if G equals 8, this is expected to be on 3. But the expectation has some things to check. Actually, Sam's probably a good person to ask whether how many of these can be expected. But this one definitely is non-zero, but it's a very subtle class, and it's non-zero. It tries very hard to be zero. And so the point is that if I look at our compact type, the first thing is, as I said, Fixum predicts a complete set of relations. So he predicts the complete structure of this algebra. Moreover, Canning, Larson, and Smith prove Fixum is correct in this case, and they have work that does more general, but at least in this case, prove it's correct. And what happens there is that in what I mentioned before, I should have said that this delta G is in codimension G minus 1. So G minus 1 here is 5. So we're interested in this pairing. This 9 is 2G minus 3, so that's the same. Here, that's 2. So this is the pairing for a compact type. And if you use these results, the dimension here is 71. And the Q vector space dimension here is 72. And the rank of this pairing, well, it can't be 72, but the rank is the biggest one for 71. And that means that there's a one-dimensional space inside here. So there's the Gorenstein firma. Those are the classes that are hiding from the Gorenstein pairing. And our shadow, pull back the shadow, lies exactly there. And this is true for all of these G's. They always lie in the kernel of the Gorenstein pairing. So they're trying to be zero, they're hiding. So actually, to prove this is not zero, you have to show that that class that's not seen by this pairing is not zero. That's a lot of particularly that requires all of this work, but it's true. And that's so this is the first place we have an interesting class which is shadow on. And I mean, there's a whole way to go in this direction, which is kind of aspirational, but there's this hope that these shadows will explain, suitably interpreted, explain all of the failure of going comparing here. That's just the hope. Okay, so that was what I wanted to say about that. It's really, there's a lot more information I don't know how to use that.
Just a question. Like you said, it's big LG minus, I mean, like the total ring of LG, but is there, I mean, is this not subjective? I mean, is it known that it's not subjective?
What's not
So,
yeah, very much non-subjective. That's why it's useful. I mean, what from the topology of this map?
No, not from L star, but from the chart.
From the child, I still think it's non-subjective, but that would require some work. I still think it's non-subjective, but it requires some. But certainly from the topology. Okay, so maybe I come to this question which I left out. What is the projection? And then it's kind of natural to then consider what's the projection of all of these. They all fit together. Well, they're all kind of the same family. Take any product locus. This is some class. We talk about the AG. And so what is it? It turns out it's very nice way to calculate it. Depends on the sorts of comfort, proportionality, and a bit of luck. So it turns out there's a very nice formula. Which I'm going to write pretty much I'm just going to write the formula. And if you want to know more about it, you can paper as that. But it requires, so it requires this. This is why I'm with you from the past, the formula where is the 1,000 pages. This will only say something again about. Also, I should say that while we expect that the shadows of these product loci, many of them are not zero. That's what I would expect. I would expect in most of them. This is the only one we know. So if you have a new idea about how to show it, you're very happy to hear it. Okay, so the next I want to just write the formula. We don't have time to talk about it. Okay, this is also a weekly paper with Sam Fanning, because the junction. So we use the notation here to G. And each one of them at least one. Star and star I. Okay, so what this is there's some constants here. These are the same constants that appear. This is exactly Van der Geer's calculation evaluation of that generator. So there are a bunch of products that we're doing. Then lambda G minus 1. So I start multiplying by descending and then until I get to G star plus 1. G star is to myself. And then I have a determinant, and it's just a short determinant. So then the T and so it's a short determinant, so I just have to tell you what the indices are. These beta indices for the short determinant. And this comes, so there's some beta. And you can see that the short determinant is related to Schubert stuff somewhere. I would put it here. So I give you the vector of integer here here. And it's a vector of length G star, and the determinant is G star with a star determinant. And I put here G star minus G1 star. And I'm giving that same thing. G1 star times. Then I put this. I just picked them and when I finish them all, I put anything exactly the total G star. You can also look at it. That's completely explicit form. So if you want to know the projection, it's just the following and explicitly give the answer to you. And so these are the Bernoulli numbers that are exactly the valuations of the generator. So you say, how does it do such a thing? And the answer is this, maybe I say one word about it. Probably don't have time. The idea is to transform this into a problem about the ground of your mind. That's where the Mumford principle comes in. And the heated calculus of Lagrange and Grossman is what we take the product of Lagrange and Grossman, smaller Lagrange and Grossman, equal big Lagrange and Grossman. You have to ask what the fundamental process is in terms of the lambda sphere. And this is super calculated, but why there's some super simple Schur polynomial form that this thing sits inside the P2G, and it turns out by some miracle there is this closed Schubert cell here that restricts to exactly this. And that restriction misses all the simulating by closed Schubert cell. There's a geometric statement that this cycle is pull back to the closed Schubert cell. This Rosmanian and that's the Schur formula and the plus amount. So that gives that's why. So it requires some luck. Okay, so if you want to know more, you can either ask or read look at the paper. I was going to give some examples. Probably don't have time tonight. Okay, so I want to say the last topic was the connection to the Hamiltonian. This is maybe the most surprising, and it comes from considering projections. So I've been thinking about some very simple loci, the loci of this product, but there are more interesting loci, many more interesting. In fact, this is what the talk leads to this question. You pick any nodal Lefschetz locus or any locus of using varieties, the real multiplication or anything like that, and give you some answer. But the loci I'm going to talk about are these loci here, N, L, G, P, so these are inside, maybe it's not the A, and there's an extra index here, P. What is that index? So this should be the moduli space of abelian varieties that have an abelian subfactor, E, an elliptic curve, so one-dimensional being, such that the class that we measured against the polarization is D. Okay. So this is another locus in the AG where the Nernst-Severi group has increased. And if I take P equals 1, we can check that this is none other than one we have. So the generalization of that. And so we can ask, what is the projection? Well, the question is more or less the same. What is the projection of this one? And geometric arguments show that whatever it is, it has to be a multiple of lambda 2 minus 1. I don't have time to do this. The third number times lambda 2 minus 1. So then the problem is extremely explicit. Can you calculate this number? That short determinant formula gives the answer for D equals 1. But the whole answer has a fantastically simple form. And this was calculated by Iribar Lopez. It's also here. If I write down this formula and tell you how it connects to it. But as I said, you can ask it for anything, any locus. So I would say that from the point of view of this discussion, if you have a cycle in AG, the two questions you can ask immediately is what is its chronological part, and is the non-part of the shadow not zero? Those are two immediate questions. And in the case of these basic cycles, we always get to the same one. So the calculation here are Lopez. This is the last one. Papers here also consider this number, which is the coefficient of lambda 3 minus 1. So it's given by this formula. So this is P divided D, 1 minus P, 1 minus P, minus P, 6, and here's the million. Okay, so this, there's various things to say about it. I'm not going to say much about it, but if you take the D equals P special, this connects calculations on A2 vector here. It specializes to that. And the connection that I want to say, yeah, so if you want to say how to prove it, you have to ask H1. Okay, so the connection we're seeing is that in the fall, I was thinking about this problem, but not in this way, the way that he actually solve it. It's not different to say. Suppose, DB is then, if it's tautological, it has to be equal to then I can calculate this. In the case of tautological, I can calculate it. I just write things in my neighborhood. I can just write it as an integral. It's the integral and bar, the pullback, the Torelli of this node, the Lefschetz locus, multiply by lambda 3 minus 2 to get the dimension right, and then that's the evaluation factor, and then I can normalize it. So this is a fact. If it's tautological, it has to be this, and I can write the formula. And it was my view, which is basically a philosophical view, that so I can write this is the C always this where this guy is the right side. Meaning that this is definitely this without the hat is this. So if it's tautological, it has to equal the integral. But my view was that it had to be the integral anyway, and the reason for that was that this shadow does not reveal itself in these integrals. And the reason for that intuition was because that's what we found with our extensive calculations. But anyway, that was just a leap. But and the thing that's great about this integral, we can just basically do it. If you, but that to do it requires the full theory, the local theory of curves. Somehow the two lambda factors, which means you're not mapping the curve with threefolds, it's a moving theory of threefolds, and this would take a long time to explain. The local theory of curves, this is in the form NLP, and it's related also to various homologies, but the outcome of this is these things. Each coefficients, the C, G, D, are directly expressed with -1 normal movement variance. D is here. And this process is relatively complicated. It involves it requires a lot of steps in here. You have to create descendants for relative conditions, and then you have to use the correspondence with the use someone else about scheme. But the thing that was interesting about this is that while a lot is known about the genus zero function, very little is known about the genus one, the genus one remote. But it happened last summer that KJ sang by some kind of coincidence, and we're exactly studying this problem. We found a complete conjecture for what we can see.
And, sorry, I don't understand the conjecture. So what is a CGD?
It's this interval, right? What's here is says that if it's tautological, then this equals integral. The conjecture is that it's equal whether or not.
What is then the hat of CG if it's not tautological?
It's there.
If you okay.
Solve the board. So maybe I write the formula that I can. But what has happened here is that by some kind of amazing luck, we've been working on exactly this problem, and we adjust the solution. Although that was a conjecture, we adjust the solution using calculations in the given problem. So there's two things to say. First is that A towards calculation together with this conjecture. Maybe I just stopped out on this. I won't be able to remember. So I'll say a few words. So one thing is true is to take A towards theorem, and you take the conjecture that C hat is equal to C D, and then you propagate through all the correspondence. You get exactly the conjecture that H. Sang and I made in the summer for this kernel variance equality. And that, of course, that answer in terms of the trace of the operator of quantum multiplication, the basic operator in quantum multiplication. So that's one way to say it. We 100% believe that conjecture is correct. So one way to read this is that if you believe that conjecture is correct and A towards the theorem, then that actually proves that the C hat equals C. But there's a missing piece. The missing piece is that, at least from this point of view, maybe you could say that the C hat equals C is equivalent to this conjecture for the kernel. There's a missing piece. And then the final thing I want to say is that, well, why should we believe this? Like I gave some mystical reason that the shadow will not reveal itself in the integral. There's a better way. The most optimistic thing to say here. Maybe I will right on. Which would also complete the picture. So I should say it, there's no doubt that all of that is correct. We found that from a wave conjecture completely independently using very different experiments. Specifically, this thing we'll talk about today. So there's no doubt that all those things are correct. So the only one that's actually proven is the calculation. So another way to a simple statement that makes all those things actual theorems is something that is about the nature of projection analysis. A conjecture, maybe speculation. It fits with all of our data. And the person that occurs to actually say this, it's a good goal of the paper. And it's with that, and this is with the projection now. So it's defined as an additive amount. Defined using your algorithm. So this is this is a kind of cool statement if you believe it, and I'm not 100% sure I believe it, but it certainly, if you believe it, it actually makes all that stuff true. You know, it makes the middle one. I don't have time to explain what it is. And then if you go back and check where we can use projection, it's always in fact ring. So we cannot contradict it. So it'd be great if someone had some idea how to do this. Totally type of thing. And technically for the connectionality scheme, you don't need such a strong fit. Like you can say if the ring homomorphism on some sub-algebra of some nice classes, but this is really the clean one fit. Okay.